the previous problems that we solved all had solutions for them, and they all had exactly one solution. And we interpreted it as intersections of lines in the 2D case and intersections of planes in the 3D case. But that's kind of going to get a lot harder because you can have a system of equations that has 4 variables and 4 equations. So essentially it lives in 4-dimensional space. So then you have to think of 3-dimensional hypersurfaces intersecting in a 4-dimensional space at one point. Not that easy to visualize. But it turns out there's a still difficult, but at least alternative, most of the time easier way to visualize that is to visualize linear equations as vectors. All right? So what I mean by that is if I have, let's say, 3x minus 2y equals 4, and I have x plus y equals 7, I can write that as a matrix equation as 3, negative 2, 1, 1, right? Because 1 times x, 1 times y, times the vector x, y equals vector 4, 7. All right, and remember how this works. So when I multiply a matrix times a vector, it's this really compact way to write these equations. So the top one is row 1 times column 1. So we get 3 times x plus negative 2 times y. So there's my 3 times x minus 2y equals the top row 4. In the bottom row, I've got 1 times x plus 1 times y equals 7. So bottom row times the vector, I get 1 times x plus 1 times y equals 7. All right? So you can interpret this as lines, right? So these aren't the real lines that I'm drawing, but let's say you have x, y. Then example is I could have a line doing this and a line doing that, right? And then I have an intersection point where they both are simultaneously satisfied. So this would be a solution to a linear system that represents these lines. I just made these up. I made these up. They aren't related. But you don't always have a solution. So what if you had something like this? There aren't that many options in 2D, but what if you had a line like that and a line like that, where they're parallel? If they're parallel and they're separated, you're never ever going to have them touch. So there's actually 0 solutions to this equation. So one solution in here we have 0 solutions. All right, that's not terrible to visualize. And then you also have an option where there's actually an infinite number of solutions. So to get infinite solutions, right, I had 2 lines that had different slopes. If they have different slopes, they're going to intersect, because if you go far enough along, somewhere they're going to intersect. But if they're parallel and separate from each other, meaning they have the same slope but different shifting vertical shift factor, then they're never going to touch. There's no solution. But here, what if you have the exact same line? Let me see if I can make it bold or something. All right. Kind of worked. What if you have the exact same equation twice, right? So 2 lines. You know, lines parallel and the same, equal. So then you have an infinite number of solutions, because that's a solution, and that's a solution, and that's a solution, and that's a solution, and that's a solution, so you can have infinite. All right? And those are going to show up in different ways through the matrix equations that we solve. We'll get to that in a chalkboard or two. So this isn't terrible to visualize, right? They're either, they cross each other, they're parallel, and they're separate, or they're parallel, meaning same slope, and they're right on top of each other. I think I'll change that to on top of each other. All right, so those are the only options when you have lines. What about when you have planes? That gets a little more complicated. Now for planes, it's a little more, there's some more cases, right? You have 3 degrees of freedom now. So I think I'll start, I pre-made this. So again, we have, system of equations. Since it has 3 variables, they're going to end up being planes. And then you can translate that into a matrix equation. And right, so I get the 2, 3, -4 from there, the 1, 1, 1, 1, 1, 1 from the coefficients, and 1x plus 0y plus 4z, so 1, 0, 4 times xyz. Right, kind of just tells you the coefficients on the xyz in each equation equals the right-hand side. So before we worked this out, and we got this solution right here. So we reduced these equations, adding rows to each other to try and get zeros in certain columns places. We ended up with something like this, where the 3 planes intersect at one point. So all the planes had different tilts, but that isn't enough to guarantee you'll have a unique solution. So, let's see if I can do this again. Right, so the 3 planes could intersect at one point, and they all had different tilts. I hope you can see that wellish. Sorry, that's probably the best I can do, and here's the best picture I can draw. All right? But that's not enough to guarantee you'll actually have one solution. You could actually have infinite solutions. So that one I was able to draw. Not the best artist, but I could draw that one. So in that one, they're all intersecting, but they're all intersecting at the same line. So, all right, that one and that. Okay, I got it. So pretend that these are continuing off into infinite space, right? Then there's planes extending, kind of where my pinky's moving, but they all intersect in one line, and so there's an infinite number of solutions because you can pick anything on that line. So you could have different tilts and intersect in one point. You could still at different tilts intersect in a line with infinite solutions. You can also end up with 0 solutions even if you have different tilts. So this very difficult to make case. If you pick planes randomly, you're never going to get it. But essentially it ends up making, all right, how am I going to do this? A triangular prism, and it just goes on forever and ever and ever. And it's intersecting at the, where the orange meets the yellow, where the yellow meets the purple, and where the purple meets the orange, right? And the planes are continuing off. Purple goes that way, orange goes that way, and yellow goes that way in the plane here. And so here I tried to draw it. I did an okay job on that. It took me a while. But you could have the different tilts, and none of them intersect. So 0 solutions. So planes different tilts, you could have 1, you could have 0, you could have infinite. All right. A few more cases than just the lines. And then you could also have planes being parallel. And I think I forgot a case in here. There's another one where you could have 2 parallel planes, and then you could have another plane, let's see. That's wrong. That kind of intersects both, but the 2 planes there are parallel. And so that one will also have 0 solutions. I might be missing some cases still. But if you have some parallel planes, they could all be separated by a certain amount, so I don't know how I'm going to do this. All right, the 3 planes are parallel and separate. Pretend those are parallel and separate. Yeah, you can read the drawing. So, they all have the exact same tilt to them, but they're all separated. None of them touch. 0 solutions. You could have a silly case where 2 of the planes lie on top of each other. I can actually hold that one with my hands. But then the third one has the same tilt, but it's too far away. They don't touch. And so then you have 0 solutions. You could have infinite solutions if the planes are just all the exact same plane. They're all on top of each other. So you can pick anything inside the plane you want. So infinite. Then this one I just remembered. You could have 2 planes are parallel, but then another plane isn't. But because the 2 planes are parallel on the top and the bottom, you can never get these to touch. Right? You're never going to get all 3 planes intersecting all at once because the top one and the bottom one are parallel to each other. All right, so there's different numbers of solutions in each of these, but there's also kind of different levels of infinity. So in this one, you have infinite solutions, but they're all lying on a line. So you have kind of a one-dimensional set of infinite solutions, an intersecting line. But in this one, you actually have a two-dimensional set of infinite solutions, right? You can pick any point where all those planes are all on top of each other. And so there's kind of more solutions in this case than in this case. So then if you try to go to 4D, well, good luck with that. But there's a better way to visualize this, and it's actually visualized, instead of intersections of lines and planes, it's going to be adding together vectors. And so we'll do that next. On the last chalkboard, we investigated what the different cases are in 2 dimensions when you have lines intersecting, and then in 3 dimensions, so 3 equations, 3 unknowns, when you have planes intersecting. There were a lot of cases. I don't think I even got all the ones for the planes. And it's confusing, right? So there's an alternative way to interpret when you're solving systems of linear equations, though, and you can do that using vectors. All right, and so first off, if you don't know what a vector is, I made some videos on that. They are kind of common to a lot of different courses. So it's in the top right there that goes over vectors, you know, what they are, how to add them, subtract them, dot product, cross product, you know, cool stuff. And just watch them as needed. Maybe you already know vectors though, but now I'm assumed you watched that and we're going to continue. So let's say we have a system of equations. And I'm going to write them a little bit differently this time. So let's say, you know, normally I do like 3x plus y or something. Here I'm going to do 3 times some number c subscript 1, all right? Then I'm going to subtract from that c subscript 2. So c subscript 1, I'm going to call c1, and then c2 are just some numbers, all right? And that has to equal 4. Okay, then my second equation, I'm going to have a negative c1 plus 2c2 equals 3. Yeah, sure, 3. So I've traded out x and y here because I'm going to need x and y later when I'm writing down the vector components. But pretty much it's the same thing. I have 2 equations, 2 unknowns. My 2 unknowns are c1 and c2. Now I could write this as a matrix equation, right? I could write this as 3, negative 1, negative 1, 2 times c1, c2. So, right, so pretty much each row has the coefficients for c1 and c2 equals 4, 3. But I could also write it a little bit differently. So I could write this instead as, I could take like this first bit as a vector, plus the second column as a vector, equals the third column as the right-hand side. So to do that, I can write this as 3c1 and negative c1 plus negative c2 and 2c2 has to equal 4, 3. Right, that works, right? But I could make it even simpler, or I guess not as wordy. I could take c1 out of this vector, move it outside, and I could take c2 out of this vector and move it outside. This is the same then as, right, 3, negative 1 times c1 plus, I've got negative 1, 2 times c2. That has to equal 4, 3. So now to interpret solving the matrix, the system of equations this way, I essentially have, here's why I couldn't use x and y before. So we're on the xy plane. I have a point I want to get to. The point is 4, 3. So let's go ahead and make this 5. So 5, negative 5, 5. So then the point 4, 3 would be like right there-ish. I want to get to that point, and I have these 2 vectors. I have 3, negative 1, and negative 1, 2. I can multiply them both by a constant and then add them together. So 3, negative 1, all right, that would be like right here, I think. And then negative 1, 2, All right, there-ish. Okay. So I get to multiply these vectors by scalars, so I can stretch, compress them or lengthen them. And when I add them together, I want to get to this point. So it looks like if I want to do that, I'll draw. All right, so I want to do that. I have this vector, and okay, I got to come down to kind of right here, I think. So I'm trying to make it parallel to negative 1, 2. And then I have to add a bunch of negative 1, 2 to get up there. So that kind of makes sense. So right, if I take approximately 2 times this vector, I'll get to here. Then I take approximately 1, 2, 3 times, I don't think that's the real answer, but approximately 3 times the second vector, negative 1, 2, add them together, I'll probably get to my solution. All right, let's go ahead and solve this one and see what the real solution is. So again, it's still nice to solve in matrix form, and we're going to write an augmented matrix form actually. So let's go ahead and solve this and see if my approximation was right. So I'm thinking it's about C1 is 2, and then C2 is 3-ish. All right, so let me write down that. C1 approximately 2, C2 approximately 3, I'm thinking. So let's see if that works. All right, so augmented matrix form, this is 3, negative 1, negative 1, 2, augment with 4, 3. Okay. And let's see, so we're going to take, all right. I'm going to take row 1, I'm going to add that to 3 times row 2. Then I'm going to put that in row 2. The reason I'm doing that, I try to avoid fractions whenever I can. So here we go, let's do it. So the top row I'm not changing, I'm only changing R2, so I'll still have 3, negative 1, 4. The bottom row I am changing, so I take 3 plus 3 times negative 1, so I get 3 plus negative 3. I get 0. Then here I get negative 1 plus 3 times 2. So negative 1 plus 6 is positive 5. Yeah. And here I get 1 times 4 plus 3 times 3. Okay, so 4 plus 9, I think that's 13. Yeah. Okay. So then I can go ahead and solve from there. So from that, I know that C2 times 5 equals 13. So that's going to mean C2 is equal to 13 fifths. Right. If I take 13 fifths times 5, then I'll get 13 equals 13. And oh boy, all right, then C1, let's go to the other equation. So I have 3 times C1 minus C2, but I know what C2 is. C2 is 13 fifths, equals 4. Oh joy, all right, so what if I multiply everything by 5? So I get 15 times C1 minus 13, right, times 5 equals 20. And then I subtract I add 13, so I get 15 times C1 equals 33. So then C1 equals 33 over 15, which I'm pretty sure is, okay, if they both have 3 in common, so it's 11 over 5. All right, I did okay-ish. So 13 fifths, that's almost 3, right? 15 fifths would have been 3. And then 11 fifths, well, that's almost 2. If I subtracted 1 fifth, I would have gotten 10 fifths. That would have been 2. But that's the idea. So now, instead of solving for intersections of lines, we're solving for, okay, I've got some vectors. I get to add them together, and I get to multiply them by any numbers I want. How do I get to the point I need to get to which will end up solving the system of equations. All right, it's a little easier to wrap your head around. So now let's look at what that means when you can't solve something like that. So let's say I've got if two lines are, right, in the old one, if I had two lines that were tilted, then that's going to equate to essentially I have two vectors that aren't parallel with each other. All right? So vectors aren't parallel. So in this case, these vectors aren't parallel, right? 3, -1 is not parallel to -1, 2. There's no number I can multiply vector 3, -1 by to get the vector -1, 2. So then you have one solution. In this case. But what if the vectors had been parallel? And let me just draw, those two vectors aren't parallel. You can add those two vectors together to always get to any point in the plane, because I can travel in this direction, then I can kind of go that way. I can get to any point in the plane if I add up those vectors correctly. But what if the vectors are parallel? Well, if they are parallel, then sometimes I'll be able to solve, sometimes I won't. So let's say I have my two vectors. So this one, and they could be pointing in the same direction, or they could be pointing in opposite directions. And I need to solve for that point. And let me emphasize here. So this is the line that those vectors lie on. And let's say I have to solve for this point. I can solve for that point. It is possible, right? So I could actually take, 0 of this vector, then 1, 2.5 of this vector here to get to this point. Or I could take -1.2 times this vector, and I could get there and add 0 of this vector. Or I could add them together and, let's see, if I did one of these and maybe -1 of these, I might be able to get to that point. So there's infinite solutions. Infinite choices for adding vectors, for getting a solution. I'll call this point P. All right. All right. But another option could have been, that's not very likely that my vectors are both lying on the same line and the point I have to solve for is lying on the same line. But what if I had this one? What if I had the vectors are parallel? So here, let's see. All right, like that. And the other vector is like that. So I can solve for those. That's the line they lie on. And what if I want to solve for P? It's impossible, because I can only really, if I multiply this vector by a number, I end up on this line. If I multiply this vector by a number, I end up on this line. If I add the two vectors together, I end up on the line. There's no way to solve for P. No solution. Can't solve for P. Can't get to P. The point P. All right, so that's the idea in this one. So instead of, this one kind of corresponds to the lines didn't have the same slope, so they were always going to intersect. This one corresponds to the lines are parallel, so you have an infinite number of solutions in some cases, or 0 in another. And in this case, the lines are parallel, but they're separate. That's kind of this. All right, so that's about as equally complicated as it was for imagining solutions of the system as the solutions of intersecting lines, or not, parallel on top or crossing. And it's going to be a little bit nicer if we look at rows, though. If we look at we look at a three-dimensional space, where we're looking at intersections of planes. Similar to how we could translate systems of lines intersecting each other, we can translate, system of three equations, three unknowns, into vectors. All right. So I made this up. We're not going to solve it. All right. 3c1 minus 2c2 plus c1 and so on and so forth. All right. And you can write it like this, where this is a c1 coefficient column, c2 coefficient column, c3 coefficient column. We can also write it as vectors, right? If we do, I have 3, 4, negative 1, all times c1 plus, I've got negative 2, 1, 3 times c2, and they're the same columns as over there, plus I've got 1, 1, negative 1 times c3, and that all has to equal the right-hand side here, which is vector 1, 2, 3. Okay, so now visualizing what happens when, let's say you can't solve it. So, let's see. There. Okay. So right-handed coordinate system, right? Yeah, okay. All right, let's say you have a plane you have these three vectors. So I don't know exactly where they point. I'm just going to draw some vectors. So let's say we have, one going that way. We have one going that way. We have one going that way. I don't know. They all go in some unique direction. All right, so meaning that you can't create one of like a third vector from the other two. You can't. They're all unique somehow. You can't create one of them from the remaining two. All right, so in that case, right, you have, let's see, where's that one? Right here, okay. You got x, y, z space, right? And you've got three vectors. Oh dear, let's see how this goes. And they're all pointing in slightly different directions. Or at different directions, right? So there's no way that I can, create this one here, the longest one, from the two shorter ones. All right. So that's when we're going to have a unique solution, is somehow these three vectors all point in unique directions in XYZ space. Okay, well, when do you not have a unique solution? Well, they're not unique if somehow you can create the third from the other two. All right, so for that, I'll get a plane. The white one's good for this. So what if you're in XYZ space, and pretend this is in XYZ space. I can't hold that many things together. And you've got, oh, maybe I can. Then you've got one vector pointing this way in this plane. You've got another vector in the same plane. Well, that's not that bad. So, any two vectors are going to be in some, any two vectors are going to be in some plane, all right? And this plane is in XYZ, three-dimensional space. I have one of my vectors here, one of my vectors here. Any two vectors, I can always fit them in a plane. But most of the time, if you have some vectors, and you have two of them that fit in the plane, if you have three random vectors, though, pretty much zero chance you're going to be able to fit them all in one plane. All right, so by adding these two vectors together, the yellow and the purple, you can get anywhere in this plane, right? You take some scalar times the purple one, take some scalar times the yellow one, add them together, you can move anywhere you want in the plane. So if the orange one also lies in that plane, then it's possible that you can use the purple one and the yellow one to do whatever orange can do, to go wherever orange can go. But if orange is not in that plane with yellow and purple, then in a sense it points in a unique direction. There's nothing, you can't create the direction that orange points in by using the directions that purple and yellow point in. It's just not possible. So in the case where they all point in unique directions, we can solve the system of equations, always. But if they're the case where they're all in the same plane, which is called coplanar, oh, come on, then you can solve for things in the plane, and there will be an infinite number of solutions in the plane because you have a choice of which two vectors to use, pretty much, or all three, and you have multiple ways to get to the same point somewhere. But if the point you're solving for is outside the plane, there's no way to add these vectors together to get outside the plane because they're all stuck in the plane. No matter how many multiples and ways you add them together, there's no way to escape the plane if they're all stuck there. All right, and then the silliest case is when all your vectors in three-dimensional space, come on, all the vectors in three-dimensional space point the exact same direction. So now, instead of a plane that you're stuck in, you're really stuck on a line. All right? And so instead of the confusing cases that we had to deal with in the interpretation where we're looking at the intersection of three different planes, if we're looking instead at summing together three different vectors multiplied by these scalars, C1, C2, C3, we can interpret what happens when we can get a solution versus can't, and so on. So if I draw that out, let's say vectors pointing vectors, and I'll say the column vectors, because each of the vectors is formed from one of these columns. I know all point in unique directions, all of them. Directions. That's going to mean you can always solve all, and there's exactly one solution. All right, but in the case where they're all coplanar, coplanar. Okay, we're going to have to trust my artistic ability. Not something I'd recommend anyone ever do, but here we go. Okay, I'm going to have you go right there. Then both of you are going under. Okay, and let's say the three vectors that we have. This is why I used my little art projects, little craft projects. If they're all coplanar, I think that's how you spell that. Then you either have, zero solutions, meaning that would mean that the points that you're trying to solve for, so I'll do here, point P is outside of the plane, zero solutions for point P, or let's say we have point Q inside the plane, you actually have an infinite number of solutions. Which essentially is like an infinite number of choices, an infinite number of ways to add together the three vectors to get to Q. Right, so you could have zero, you could have infinite. But you only get infinite if you're solving for a point in the plane because all three vectors are coplanar, they're stuck in the plane. The other option is you could have collinear. So that one I think I can draw fairly well. Can I label those? Yeah, whatever. So let's say we've got a vector pointing that way and another vector pointing that way, so same vector, and then another one pointing that way. Then the column vector is collinear. Are collinear. I think that's how you spell it. Then let's say we've got our point. Okay, let's say point P. I'll stick with that one. So let's say we have Q and we have P. There are going to be zero solutions for P. or there's going to be infinite solutions for Q, because Q is in the line. There's an infinite number of ways to, add together these vectors. And you could just take some number times the first vector here, you could get it directly to Q, or some number times the second, get directly to Q, or some negative number times the third to get directly to Q. There's an infinite number of solutions. All right, and just to be clear from last time, I don't think I said it in here, but essentially the point P we solve for is the right-hand side of the sum of the columns here, right? This thing 1, 2, 3. So in this case, no matter if the vectors are pointing in unique directions, they're not collinear, they're not coplanar, then no matter what I have on the right-hand side, if these three point in unique directions, they're not coplanar, not collinear, I can always solve for it. If the three vectors are coplanar, then they can solve for right-hand side points that lie in that plane, and they can't solve for right-hand side points that lie outside the plane. And if they're collinear, then again, you can't solve for right-hand side vectors, points here, that are outside the line that all three vectors lie in. But you can solve for points that are right-hand side points that are in the line, right? And no solutions versus infinite. So that's a lot easier to wrap your head around than the planes intersecting and stuff. It'll also be conceptually easier later on when we're dealing with more equations like 4 and 4, so 4 unknowns, 4 equations, and also a bunch of theory and why things work and deriving stuff like the null space. And so just to emphasize that, let's go and do a 4-variable, 4 unknown system of equations. For a system of 4 equations and 4 unknowns, if you're super duper amazing and you can visualize 4-dimensional space, that's great. For the rest of us, we can't rely on that, but we can rely on intuition from 2-dimensional and 3-dimensional space, okay? I got a little lazy with this one, so the coefficients just goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 19, 18, 19, 20. So 4-dimensional space, we're going to have 4 vectors in 4-dimensional space. We have a 4-dimensional point in 4-dimensional space. You want to know, can you get to that point? Can you add up these vectors in some way to get to the point in 4-dimensional space? So just to emphasize that, all right, C1 plus C2 plus, you can see also, if we had done this, X, Y, Z, I ran out of letters, this is why we use subscripts on the variables. So C3 plus, I'm going to make it here, C4 plus, okay. Oh, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, cool. Oh, sorry, that's an equals. All right, so we can't, there's kind of collinear, coplanar, that's a little more confusing now. But really what they all shared before, you could either have a solution, and you have exactly one solution, if all 4 of these vectors point in some unique direction from each other. All right, it's meaning they aren't going to, if they're not pointing in a unique direction, then somehow you could combine 3 of the vectors to make the 4th, something like that. All right, but if somehow they're all unique, you can't, some unique direction to them, then you can't use the other 3 vectors to make the 4th vector, all right? So if all 4 vectors are, it's called linear independent, I'll get to that later, but if the 4 vectors, if I'll say all the column vectors, are somehow unique, point uniquely from the remaining 3 in a unique direction. from the other three. That's not a very precise definition. They're all pointing in different directions, but it's that you can't create one of them out of the remaining three from the others. Then there will always be a unique solution. I'll say there will always be exactly one solution. All right, and we're gonna have to figure out, how can you tell if they're unique or not, and that's actually through row reduction. But if the columns, one of the columns vectors can be created from the others, then, I guess that's an S, there's either zero solutions or infinite solutions. I'll say infinite. I'm missing a bunch of letters in there. Infinitely, I think that's spelled right. Many solutions for, yeah, sure, depending on the right-hand side. Okay, so kind of going along with that, so if you're in three-dimensional space and you have vectors pointing kind of in three dimensions uniquely, you can get to anywhere in three-dimensional space. If you're in four-dimensional space and somehow those four vectors point uniquely in a way so that you can reach anywhere in four-dimensional space with them, then you can solve for any point. But if they don't point uniquely, they essentially, kind of like when three vectors are stuck in a plane, you could have four vectors stuck in a three-dimensional slice of four-dimensional space. Right? It's kind of like in three-dimensional space, one plane is a two-dimensional slice of three-dimensional space. In two-dimensional space, a line is a one-dimensional slice of two-dimensional space. That logic kind of continues up. All right, so that's the idea. So now we're going to look at, how does this actually show itself? And it's going to show itself through the row reductions. Some stuff is going to happen. Namely, we can get things like a zero row, or we can get something unsolvable like 0 = 4, things like that, and we'll do those on the next chalkboards.